Hello, my friends. As you remember, we have you have watched the videos that we did before, and today I will try to summarize what we have done last two videos. As you know, Operation Research, the code ES-308 for distance learning students. We said that Operation Research is quite important issues because we have to use our scarce resources effectively. And we said that the real world system, we said there is a real world system, and we have this is the real world, and this is the case or a problem. And what we said, we take that case, that problem, and make it model. And last lecture, we have seen how we make this model as linear programming form. And today, we'll continue on that subject. And now, you know that Operation Research has some steps. One is, let me remind you, one is to define the problem. Define the problem is the first step. Steps or main phases, steps in Operation Research. And we define the problem is the real problem itself. We defined the example, as you remember, last lecture. And the second one is to make its model, linear model, as we have said last lecture, which is the modeling. Construct the model, construct the model. This model, as you know, is the mathematical model, consists of many mathematical expressions. And today, we are going to see the first step, which is the solution of this model. Solution. To find the, as you remember, we have talked about the optimal feasible solution by using, there are many methods. One is the graphical solution method, and I'm writing over here the first step as solution using graphical solution method or technique. So let me write the example and study on it. I'm going to erase this part and write the model. I'm going to take the same example, that is the Rademacher example. It is the producing paints, and the final problem was like this, and you can follow this from Taha's book. I've sent the from USEM, and you can watch that one also, which is it was the maximization type problem. Maximize, let's say z was equal to 5x1 plus 4x2, and this is subject to the constraints. As you know, we have the raw material one, which is the 6x1 plus 4x2, which is smaller or equal to 24. And the second one is x1 plus 2x2, smaller or equal to 6. And the x1 plus x2 smaller or equal to 1, x2 smaller or equal to 2, where x1 and x2 should be non-negative. Now, let me say you how we are going to move about that one. First, we have to find the feasible solution region, all the feasible solutions. So, first, find the feasible solution space or region. How we are going to do this? We are going to use use only constraints to find the feasible solutions, all the feasible solutions. You remember that one is the raw material M1, that is raw material M2, this constraint. These two are the demand constraints. And you know how many decision variables we have? We said that we have two decision variables. You know what they are. You know, X1 is the exterior paint, X2 is the interior paint, and Z that we use is the total profit, daily total profit. Now, we are going to use graphical solutions, so we need a graphic. Due to that, we have two variables. This is the horizontal axis, which is X1, and that is the X2. That is, X1 means exterior paint, tons per day, and X2 is the interior paint, again, tons per day. So, how we are going to draw? We take that one. You know, if it is smaller or equal means two aspects, that is, it says that it is equal and or smaller than. So, due to that this is space, first we have to find the straight line. You know, that shows us space, area, and that shows us line. Don't forget this. So, assume that all these constraints are equality form. This is the assumption. So, if we assume that 6x1 plus 4x2 equal to 24, that is a line, and we have to draw a line, we need 2 points on it, and we join them. So, if x1 is equal to 0, x2 will be equal to, or should be equal to 6, and if x2 equal to 0, the other should be 4. So, to draw this over there, 0, 6 means x1 is 0, and the other is 6, and 4 means it is over here 4, 0. So, if we join these 2 points, let me join them like that, it means this equation. But our equation is smaller or equal to which side? We use origin as checkpoint. This is a checkpoint. If 0, 0, if 0 plus 0 is smaller than 24, it is okay. It satisfies. So, it means this one. And x1 greater than 0, it means that side. x2 greater than 0 means it is up there. So, at this moment, this area is feasible solution area for the first one. Second one, assume again that this is equal to 0. So, we are going to say if x1 is equal to 0, x2 will be equal to 3. And if x2 is equal to 0, x1 should be equal to 6. So, it means the point over here, which is 3, 0, 3, and that is 6, 0. So, if we join these 2 points, we get that line. This is the, let's say this is the first constraint. That is the second constraint. That one is the second constraint. Which side? Again, we are going to use checkpoint as 0, 0. Is 0 plus 0 smaller than 6? Yes. So, it means this side. But for feasibility, as you remember, last lecture we said that all constraints should be satisfied. So, now only this part is not anymore, and this part is not anymore feasible. Only these are feasible. But still we have some more constraints. So, this one, minus x1 plus x2 is, so it is, if x1 is equal to 0, x2 will be equal to 1. If x2 is equal to 0, x1 should be equal to minus 1. Minus 1 multiplied by minus, it will become plus and equal to 1. So, it will be that one, and let's throw this one. 0, 1 means 0. 1 means over here, this is 1. Minus 1 means over here, minus 1. Let's join these 2 points. Continue it like that. This is the third constraint. And which side? Again, use this origin as checkpoint. Is, you have to ask, is 0 plus 0 smaller than 1? Yes, 0 is smaller than 1, so it means this side, it means that side. Now, this part is not anymore feasible, only this part. Okay, let's continue, and last one. If x2 is equal to 2, assume it is so, it means that x2 equal to 2 means 2 is over here. It is a line. Don't forget, line over here, that is 2, and join that one. Now, let me shade the area quickly. All the constraints are toward here. It is smaller than this way. So, this area in name A, B, this is C, that part D, E, and that is F. A, B, C, D, E, and F is the feasible solution region. All the solutions in that region, including 0, are feasible. So, the first, find the feasible region by use only constraints. In order to find optimal feasible solution, it is the second step. Second step, optimal feasible solution. How we can find optimal feasible solution? We find optimal feasible solution by using objective function. Where is our objective function? It is 5x1 plus 4x2 equal to z, which is the maximization type problem. Don't forget, it is important, maximization type problem. So, for that one, let me say one thing. We call these A, B, C, D, E, F as the corner points, which is the feasible corner points. It is just corner points, corner points are the points that we are generally and always, it is the optimal feasible solution. Either we look A, B, C, D, E, and F points and check which one is the optimal, or we use our Z, which is, let's say, we cannot draw that one. Give any number to Z. Let's say, instead of Z, that is equal to, let's say, 20. What it means, now we can draw it. If x1 is equal to 0, x2 will be equal to 5. And if x2 is equal to 0, x1 should be equal to 4. Point. And let's draw this line over here. But let me use green one, blue one, sorry. 0, 5. 0, 5 is over here for 5. And 4, 0 means over here. So, if we join these 2 points, it means that that is the Z1, which is equal to 20. So, if the problem is maximization type problem, we shift, this is for maximization, shift objective function away from origin. So, as far as you can. So, if we shift it over here, we shift up to here, and that is the last point, C point, and we cannot shift more because we go outside of the feasible solution area. So, it means that point C is the optimal solution over there. Optimal feasible solution. Don't forget, optimal feasible solution. The best solution, what does it mean, optimal feasible solution? It should be feasible and it should be best among the feasible solutions. So how we can find the values of optimal at C over here? What is the value of x1? What is the value of x2? And what is the z, which is they are optimal. To find this, we have, let's say, let me show you over here. I'm erase this part. Use these lines, they are the equations. Line 1 is that one, which is the second one. It is x1 plus 2x2 equal to 6. And the other one that is intersecting at C, intersecting, it is the 6 x1 plus 2x2 equal to 24. How we can use this? We solve them together. How? If we multiplied this side, which side? This side by, let's say, this one by minus 1, both sides, that will be minus x1 minus 2x2 equal to minus 6. So this is over, and we sum them up. We get what? 5x1 equal to 20, that is 18, and this is x1 minus, which one it is over there. We find the value, if you solve them, you find the value of x1 as, let me say you over here, after the solution, if you try, you will find them at the optimal solution case. Let me find and say you the solution what should be. Okay, now let's do together. Last few minutes we have to do it quickly. This one is 6x1 plus 4x2 equal to 24, and the other is x1 plus 2x2 equal to 6. So we have to multiply this by minus 2, sorry for it, and we get minus 2x1 minus 4x2 minus 12, and from here 4x1, these cancel each other, this cancel that one, and 24 minus 12, it will be 12, and from here we get x1 as 3. It means 3 tons. If that is 3 tons, we found that one as 3 tons, and the equation over here, any one of it, x1 is 3 plus 2x2 equal to 6. x2 will happen, we take that one other side, 3 divided by 2, which is 1.5 tons. And if we put these at our objective function over here, 5 multiplied by 3 and 1.5 multiplied by 4, it means we get that as 15 plus 6, which is $21,000, because we skipped. That is the optimal solution. It means that we have to produce 3 tons of exterior paint, we have to produce 1.5 tons of interior paint, and our profit will be $21,000, and that is the optimal product mix. Don't forget, and see you. Thanks.